Optimization algorithms for operations research. Optimization algorithms lie at the heart of solving complex decision-making challenges in engineering, economics, computer science, and beyond. From minimizing costs in supply chains to maximizing accuracy in machine learning models, these mathematical techniques enable efficient resource allocation and strategic planning. Their significance grows as data complexity increases, making precise and scalable solutions essential. This guide explores foundational concepts, advanced methodologies, and real-world applications to empower practitioners navigating algorithmic design and analysis. Fundamentals of optimization problems. An optimization problem involves finding the optimal value of a function subject to constraints. At its core, the goal is to minimize or maximize an objective function, often represented mathematically as $f x $. Constraints define feasible regions where potential solutions must reside. These problems can be classified as unconstrained or constrained, linear or nonlinear, convex or non-convex. Convex problems guarantee global optima due to smooth curvature properties, whereas non-convex ones may trap solvers in local minima traps. Real-world applications range from portfolio management to traffic signal timing. For instance, airlines optimize flight schedules to balance passenger demand with fuel efficiency, illustrating the interdisciplinary relevance of optimization theory. Objective function quantifies the performance metric to be optimized, such as profit maximization or error minimization. Constraints represent physical limitations, safety regulations, budget caps, or other boundary conditions affecting solution feasibility. Categorizing algorithmic approaches. Solving optimization problems requires choosing among diverse algorithm families tailored to specific problem structures. Gradient-based methods excel in smooth, continuous domains, while evolutionary algorithms thrive in rugged, discrete landscapes. Deterministic techniques follow fixed rules leading to exact results, whereas probabilistic methods incorporate randomness to escape local optima. Hybrid strategies combine both paradigms for enhanced versatility in challenging scenarios. Gradient-based methods. Algorithms like steepest descent and quasi-Newton updates leverage derivative information to navigate solution spaces efficiently. By calculating slopes along dimensions, these methods iteratively refine approximations toward extrema points. In deep learning contexts, backpropagation computes gradients, enabling neural networks to adjust weights optimally. However, issues like vanishing gradients hinder progress in very deep architectures unless mitigated through normalization or residual connections. Conjugate gradient and BFGS variants offer faster convergence than basic gradient descent by exploiting Hessian matrix properties without explicitly calculating higher-order derivatives. Their memory-efficient implementations make them popular choices in large-scale simulations. Despite advantages, these methods struggle with noisy objectives or high-dimensional parameter spaces where computation becomes prohibitively expensive. Specialized regularization techniques help stabilize training processes in such environments. Evolutionary computation techniques. Genetic algorithms mimic natural selection principles by evolving candidate solutions through mutation, crossover, and survival of the fittest mechanisms. Populations evolve across generations toward better performing individuals matching fitness criteria defined by the objective function. Particle swarm optimization tracks velocity vectors representing exploration tendencies of virtual particles moving through search space, adapting directions based on personal and collective experiences recorded during iterations. Ant colony optimization simulates pheromone trails left by ants discovering shortest paths between food sources. Positive feedback loops reinforce successful routes while evaporating less effective alternatives over time. Though powerful for global searches, these bio-inspired methods typically require careful tuning of parameters governing diversity preservation rates, elitism thresholds, and termination conditions to achieve satisfactory performance balances. Constraint handling strategies. Many practical problems involve restrictions limiting valid solution sets. Penalty function approaches penalize constraint violations by adding weighted terms to the primary objective being minimized or maximized. Lagrange multiplier methods transform inequality constraints into equality forms by incorporating auxiliary variables, allowing application of unconstrained optimization techniques subsequently. Barrier function formulations replace hard boundaries with softened curves that asymptotically diverge near constraint limits, guiding search away from invalid regions systematically rather than abruptly rejecting candidates entirely. Hybrid strategies combining penalty multiplier frameworks with trust region methods yield robust solvers capable of addressing highly constrained optimization tasks arising frequently in structural engineering design projects involving material strength limits and geometric tolerances. Mixed integer programming solutions. Integer programming introduces discontinuous jumps complicating analytic derivation of gradients. Branch-bound algorithms partition solution spaces recursively until reaching atomic subproblems amenable to direct evaluation via LP relaxation techniques. Cutting plane methods iteratively approximate integer feasible regions by adding hyperplanes excluding fractional points detected during successive iterations. Their effectiveness depends heavily on quality of generated cuts, reducing duality gaps rapidly. Column generation techniques decompose large-scale IPs into manageable master subproblem interactions, commonly employed in vehicle routing and crew scheduling applications requiring distributed processing capabilities. Globally convergent branch price cut hybrids now tackle instances previously deemed computationally prohibitive by integrating multiple resolution phases simultaneously for improved overall efficiency gains. Meta-heuristic search paradigms beyond conventional deterministic and population-based algorithms exist. More exotic search strategies inspired by physics phenomena or biological behaviors. Simulated annealing mimics metallurgical cooling processes, permitting temporary uphill moves during early stages, facilitating broader landscape explorations. Taboo search maintains memory structures prohibiting revisits to recently explored states, preventing cycles while encouraging diversification through aspiration levels, relaxing some restrictions conditionally upon discovery of particularly promising candidates. Mimetic algorithms blend genetic evolution with localized improvement heuristics, enhancing both exploitation abilities, through fine-tuning good solutions, and exploration capacities, via novel combinations generated during reproduction events. When confronted with NP-hard combinatorial optimization dilemmas like traveling salesman or knapsack problems, these smart heuristics routinely outperform exhaustive enumeration despite theoretical worst-case guarantees remaining unproven in most cases. Evaluation metrics and benchmark suites. Selecting appropriate optimization tools demands rigorous assessment against standardized benchmarks measuring both solution quality and runtime efficiencies across varying scales. Commonly referenced repositories include CEC, Congress on Evolutionary Computation, and COCOP, Combinatorial Optimization Comparison Platform, offering extensive testbeds. Accuracy metrics compare final outputs against known ground truth values where available. Though many industrial applications lack analytical closed-form expressions necessitating comparative analyses relative to alternative baselines. Computational time remains paramount concern, especially for embedded systems or real-time control applications demanding millisecond-level responses. Profiling different implementations helps identify bottlenecks amenable to parallelization or hardware acceleration opportunities. Scalability tests reveal algorithm behavior patterns under increasing input sizes, distinguishing polynomial versus exponential growth characteristics useful for forecasting long-term viability prospects before full deployment decisions get made. Industry applications across domains. Airlines utilize network revenue management systems employing dynamic pricing models augmented by robust optimization techniques, ensuring seat availability aligns precisely with projected customer demand. Fluctuations across flight segments. In semiconductor fabrication plants, wafer assignment algorithms determine optimal placement orders considering tool calibration intervals, equipment maintenance windows, and batch size constraints inherent to photolithography operations. Supply chain managers deploy inventory replenishment policies balancing holding costs against stockout risks using stochastic programming frameworks accounting for uncertain supplier lead times and fluctuating consumer preferences. Healthcare administrators face intricate scheduling challenges coordinating surgeon availabilities, operating room allocations, and patient acuity levels requiring multi-objective formulations reconciling financial targets with clinical outcome priorities. Emerging trends and future directions. Rapid advancements in artificial intelligence are reshaping classical optimization paradigms by endowing solvers with learned behaviors, extracting implicit patterns from historical data samples rather than strictly relying on explicit mathematical formulations alone. Quantum annealing technologies promise breakthroughs in solving QBO, quadratic unconstrained binary optimization, problems exponentially faster than current digital computers, potentially revolutionizing cryptography and logistics sectors experiencing explosive growth trajectories. Automated algorithm configuration tools streamline hyperparameter selections for diverse solver classes, eliminating manual trial-and-error efforts traditionally required to calibrate sensitive settings, impacting final result qualities significantly. As sustainability concerns intensify globally, green computing initiatives seek environmentally friendly optimizations prioritizing reduced carbon footprints associated with cloud infrastructure usage without compromising service-level agreements maintained between providers and consumers alike. Practical implementation considerations. Choosing the right library or framework greatly influences development productivity and code maintainability. Open source options like SciPy, CVXPy, Gurobi, and TensorFlow cater differently depending on whether you're tackling convex programs, mixed integers, or deep learning loss surfaces respectively. Precision trade-offs become critical considerations whenever dealing with floating-point arithmetic operations susceptible to round-off errors accumulating catastrophically during extended iterative refinement sequences typical in numerical root-finding routines. Visualization tools aid comprehension by plotting convergence curves, tracking improvements observed over epochs, helping diagnose potential issues like premature saturation, indicating possible need for learning rate adjustments or architectural modifications. Parallel execution capabilities offered by modern GPUs and TPUs drastically accelerate large-scale computations, becoming indispensable features whenever facing high-dimensional parameter spaces requiring massive concurrent evaluations to find adequate local minima quickly enough. Conclusion: this survey provides insight into the rich tapestry of optimization algorithms applicable across myriad disciplines. Understanding fundamental classifications aids informed selection aligned with specific application requirements and resource limitations peculiar to particular industry verticals. To stay competitive in today's fast-evolving tech landscape, professionals should continuously expand knowledge horizons, embracing emerging methodologies while mastering classic techniques, forming solid foundations upon which innovative breakthroughs will surely build tomorrow's solutions.